All right, let's take a look at 7.5 real numbers and the real number system. Um, so first of all, let's take a look at what we mean by a real number. And then I'm going to look at organizing it in a way that might help for the visual. It's any number which can be represented as a decimal. And actually, um, yeah, I like that. All right, so if we take a look at this, the decimals we'll have to make sure we clarify. So I'm first going to do let's just take a look at this, real numbers. Okay, and I did this a little bit with you earlier in concentric circles. Now I'm going to take a look at it in a format of the following. Real numbers are divided into two subcategories. They're either called rational or they're not rational, and they're called irrational. And the set of rational numbers, again, anything that can be written as a decimal, anything, when we talked about rationals before, let's look at it this way. This is the quotient of two integers. Quotient means to divide. Integers are positive and negative whole numbers or zero. And so we can think of this as anything that can be written as a fraction. So let's see, what can we write as a fraction? Well, we could start with where we began with this class, the set of natural numbers. 1, 2, 3, the counting numbers. Then from there, we moved on to whole numbers. So that included 0, 1, 2, 3, etc. Then from there, we moved on to integers, which were positive and negative whole numbers. Then, of course, fractions. I'm just going to list them even though I don't technically need to. And that could be proper or improper fraction. And then we have decimals. But with decimals, we have to subdivide that into either ones that terminate or end. For example, 1/2. That's the same as 0.5 with 0, 0, 0. It terminates or it ends. So by definition, it can be written as a decimal. So therefore it's real. By definition, it's already a fraction. And so it's rational because that's a fraction. Or they have to repeat. So for example, 0.333 repeating in class the other day, we showed that that's the same as the decimal 0.3, which is the same as the fraction 1/3. So for the same reason, it is rational because I can write it as a fraction. It is real because I can write it as a decimal. And then I kind of want to show you, in case this comes up, real numbers, the symbol for a real number is a double strike capital R. Natural numbers we've used throughout, that's a double strike capital N, sorry. Whole numbers are a double strike capital W. Integers technically are a Z, but your author uses a double strike I. Okay, and fractions and decimals aren't necessary. I just put them in there to help us. So if that's all the rationals, then what are the irrationals? Well, remember that prefix IR means not. So it's not rational. So it's not the natural numbers, not the whole numbers, not the integers, cannot be written as a fraction, Now, it can be written as a decimal. So in decimal form, remember, ear means not. It's not terminating and it's not repeating. Not terminating and not repeating. So what kind of decimal is not terminating, not repeating? Well, I guarantee if we were together, I could show you that you can already come up with 20 irrational numbers. You just may not recognize that you know what they are. So I'll show you here in just a minute. But some examples that you might be familiar with, not terminating, not repeating. So an example might be, you might be familiar with pi, which is approximately 3.141592. It keeps going on and on and on and on and on. And so we usually approximate it at 3.14. Or Euler's number, E, 2.714. Okay? But it's pretty much anything that is non-terminating, non-repeating. So one thing I want to show you is right now, you already know several irrational numbers. You just may not know you know them. Okay, so based on some prior knowledge, here's what I want to show you. From your past, if I give you the square root of 1, what number times itself will give you 1? Well, the answer is 1. If I give you the square root of 4, what number times itself will give you 4? What's number 2? If I keep going, the next perfect square is 9, because the square root of 9 is 3 times 3, so square root of 9 is 3. The next perfect number is 16, because the square root of 16 is 4. So you'll notice our perfect squares give you these nice integer or whole numbers. But if you take a look at what's in between 1 and 4, you get the square root of 2. Well, the square root of 2 exists, but it's not a whole number. It's somewhere between 1 and 2. So if I take a look at the square root of 2, I meant to take a look at that ahead of time, but the square root of 2 is 1.14, nope, 1.414213, and it goes on forever and ever and ever. Similarly, if I take a look at the next integer, 3, and I look at the square root of 3, it's approximately 1.73205, and it goes on forever. I could keep going. What do you think the next irrational, non-repeating decimal is going to be? It's going to be whatever fills in between these perfect squares. So the square root of 5, square root of 6, square root of 7, square root of 8, all of those are going to be irrational, continuing on. So any square root of a non-perfect number is also irrational. So you could put that down here as another example. So if I were to go back to how I started the lesson and say, I know that you know at least 20 irrational numbers, well, you might have known pi, but now you could go and fill in anything that's not a perfect square. Okay. All right, so what we're going to take a look at is we're going to take a look at working with radicals, just because we'll figure out if they're rational or irrational. So let's work at simplifying what are called radical numbers. And then we'll look at some application of using some square roots in particular. All right, so let's take a look at radicals, because they are real numbers. They're just either rational or irrational. Okay, so let's take a look at radical numbers. First of all, academic language, we have a radical sign. It's not a division sign because it's got this little hook on the end. Whatever's on the inside of this grouping symbol, we call the radicand. So for order of operations, this would be considered a grouping symbol, like a parenthesis or a bracket. And then inside this little symbol, you could have a number, and that's called the index number. Index number. That tells you how many roots you need before you can kind of tells you how many factors you need. Okay. And then we need what's called a principal root, because we're going to start with elementary school. Elementary school only deals with principal roots. Principal roots are the positive roots. And I'll show you what I mean in just a little bit. Okay. Principal roots occur when you have an even index number. So let me give you some examples. Let's say I ask you for the square root of 25. The square root, that's the smallest root we can have, so we don't need to write a 2 down for the index number. It's implied that it's a 2. And so what we want to know is what factor, how can we break 25 down into 2 identical roots or factors? And we would have 5 times 5. Since the index number is a 2, and we have 2 that are identical, that can come out, and our answer is 5. And the only factor that would be left over on the inside is a 1, because 1 is a factor of everything. So if you were to ask your class, okay, what is the square root of 9? Our answer is positive 3, because this is the same as 2 identicals, factors of 3 times 3. Since I have a pair of them and the index number is 2, I take that pair out, and it's that one number that we see twice. So let's say we have 16. And some of you right away know that the answer is 4. But somebody in class or your students say, well, teacher, that's the same as 2 times 8. Well, do we have any identical factors yet? No. So I'm going to factor the 8 as 2 times 4. Well, now we have a pair. I'll come back to that. Can we do anything with the 4? Sure. We could, now remember, we already have this 2 times 2 right here. I could take that 4 and make it 2 times 2 again. Now I have another set of 2s. So the first one comes out, the second one comes out, and that's another way to show that the square root of 16 is 4. Now, of course, you could have had a student go straight to the fact that this is 4 times 4. And if they see that right away and they pull the 4 out, you get the same answer. It doesn't matter which way they happen to factor it down. You'll end up with the same result. Well, does this always work? Absolutely. Let's say, for example, I give you something that is not perfect. Let's say I give you 18, and I want the square root of 18. Concept is absolutely identical. That's the comforting part of mathematics. I'm looking for 2 identical factors. So if I do a factor tree, I get 9 times 2. Now, if I'm going to keep doing it this way, and then I'll show you something else. I could ask, well, I don't see anything that's identical yet, so I'm going to factor the 9 down to a 3 times 3, and then I have the 2. Since the index number is a 2 for square root, I'm looking for 2 identical factors, and that can come out. but there's one still trapped on the inside, so it stays on the inside. And your answer is 3 root 2 or 3 radical 2 or 3 times the square root of 2. Somebody else might have noticed, well, wait a minute. I know that 9 is a perfect square, so I could write this as the square root of 9 times the square root of 2, because you can multiply in any order, and I'm just using the associative property to group them the way I want. Well, the square root of 9 is 3, and so we're still left with 3 times the square root of 2. So you're allowed to factor it any way you like, and if you notice a perfect square right away, you can go ahead and do that. So what if I gave you this one? Square root of 25 over 16. Well, if you recognize that those are both perfect squares, you're pretty much done. So you have a couple ways you could do this. You could say the square root of, when in doubt, work it out. And now you may notice that we have 5/4 2 times. So therefore, our answer is 5/4. Somebody else might go, wait a minute, division is simply multiplication, multiplying by the reciprocal. So we could have said, since this is multiplication, I can use some of the properties. So I could have split this up as square root of 25 over the square root of 16. And as long as there's no radical sign left in the denominator, you're fine. 16 is a perfect square. And so we're left with square root of 25 is 5, square root of 16 is 4. So as long as there's no radical left in the denominator, you're fine. Okay. Now, more advanced, right now, notice the radical sign is in the problem to begin with. So therefore, I have the principal root because the index number is even. These are all square roots. Now, in pre-algebra and algebra, if I ask you to solve and I give you x squared equals, let's just go x squared equals 49. Well, that little 2, this 2 tells me I'm going to have 2 solutions. That's what's called the degree. It's going to tell me I'm guaranteed 2 answers. So if I have x squared equals 49, and I want to undo the square to figure out what the answer is, to undo a square, we take a square root. But whenever you physically take a square root, you're going to get 2 answers, positive and negative. Square root of x, well, that's just x times x. Square root of 49, that's simply 7 times 7. Here I have a pair of them, so I can pull out the x. And I'm left with a positive or a negative 7 when I take that 7 out. Because we know when we check it, if I let x equals 7, then I know x squared equals 7 squared, so x squared is 49. But if we let x equal negative 7, following the same check, x squared equals negative 7 squared, well, a negative times a negative is still going to give me a positive 49. So the only time you get 2 solutions is when you physically are the one to take the square root to solve the problem. If the square root's in the problem to begin with, like what you're going to see in 5th grade and 6th grade, we just want the positive answer. It's called the principal root. Right? Now, that index number tells us how many roots or how many answers, not wrong answer, how many roots we're looking for, how many factors have to be identical. I'm going to leave a little line here because I'm going to come back in just a moment. Let's say our index number is larger than 2. Let's go to 3 to start with. So let's say I ask you to simplify. So there's not going to be an equal sign. The cubed root of 27. Well, that index number is now a 3. That index number tells me I'm looking for 3 answers that are identical, 3 factors that are identical. So 27 is 3 times 9. Well, I can keep going on cubed root. I can keep going with my factor tree. There's going to be a lot of 3s. Sorry about that. 9 is the same as 3 times 3. That index number says I need 3 factors that are the same. Well, now I have 3 numbers that are the same, so that can come out, and I'm left with the number 3, which I saw 3 times as a factor. Let's do it again. Let's say I want the cubed root, let's do 8. Well, following the same idea, if I factor 8 down, that's the same as 2 times 4. But 4 is the same as 2 times 2. And so now if I'm looking at my index number is a 3. So that means I need 3 identical factors before they can come out. They're all chained together, and they can only escape when they're in groups of 3. So what number do we see 3 times? We see the number 2. But let's say I asked you for the cubed root of -8. Okay. Well, I can't have a square root of a negative because a negative times a negative will always give you a positive. But a cubed root, I already know 8 is 2 times 2 times 2. But I could have -2 times -2 times -2 because 3 negatives are still negative. So if that index number is odd, remember I can have an odd number of negatives to produce a negative answer. So in this case, what number do we see 3 times? Well, we see the number -2 3 times. So a cubed root or a 5th root can be negative. So let's say we wanted the cubed root of -16. Our index numbers are 3, so we need 3 identical factors. 16, I'm going to come back. Let's see, this is a -1. 16 is 4 times 4. Well, that's not 3 identical factors yet. So I'm going to keep the -1 there for a moment. I'll come back. But 4 is 2 times 2. And 4 is 2 times 2. So ultimately, I still have a negative. And notice, I just need an odd number of these to be negative in order for 16 to be negative. So I'm going to rewrite this as -2 times -2 times -2. That's going to give me a negative result. And I'm going to leave this last one positive. Negative times a negative is positive, times a negative is negative. 2, 2, 2, 2 gives me 16. So I have the same result on both sides. Now, however, I have an index number of 3, which means 3 identical factors need to come out. So I'm going to bring out the -2. And whatever's left over stays in the radicand. So the cubed root, and the only thing left is a +2. So that index number tells us how many have to come out. If the index number is odd, and I could do the same thing with the 5th root or the 7th root, if the index number is odd, you can have negatives. Okay. So I'll just sort of sum that up. If I have an index number, here we have nth roots. If I have an even index number, 2, 4, 6, etc., then the result will be a positive answer or principal root, square root, 4th root. If, however, that index number is odd, I can end up with a positive result, but I can also end up with a negative result. So I can end up with positive or negative. Can be positive or negative. Because remember, an odd number of negatives is still negative. I'm going to do this a little out of order from the book because I want to take a look, since we're looking at radicals, another way to read them. Another way to read them. Then we'll practice mainly square roots, but I want to take a look at this radical idea again. Okay, so I'm going to go back to this idea of a radical. I'm going to write it again. So a radical number, I'm going to write it again on purpose. Can also be written using a rational, remember that's a fraction, exponent. So let's start with the following. Let's say we have the square root of a to some number, n. You know what? I'm going to actually back up one step. I think I want to do it this way. Sorry about that. I decide, let's do it this way, because then this will work for all of them. Let's say we have our index number is some natural number, 2, 3, 4, 5. And our radicand is whatever it is. Whatever the index number is, whatever the index number becomes our denominator of our fraction. Whatever the power is, in this case, this is x to the first, that becomes our numerator. So the nth root of x to the first is the same as x raised to the first over the index number, x to the 1 over n. So let me do it again. Let's say we have some natural number, and this is x raised to the a power. Then this is the same as our base x, whatever's on the inside, whatever power of the x is the numerator, whatever our index number is the denominator, a over n. Or you could have written this as x to the 1 over n. Oops, I forgot the x. All of this is raised to the 8th power. So I'll show you what I mean with some examples. So, for example, if I ask you to simplify 16 to the 1/4 fourth power. Notice I write it with a vertical fraction with a horizontal line instead of, I don't do this. I don't make it a slant. Okay, keep it a horizontal line, 1/4. What does that mean? This literally means whatever the denominator is our index number. Whatever the numerator is our power. So this literally means the fourth root of 16 to the first. So I'm looking for 4 identical factors. So 16, 4 times 4. I don't have enough factors yet. So if I keep breaking it down, 4 is 2 times 2. 4 is 2 times 2. So since the fourth root, we're looking for 4 identical factors. Well, there we have them. We have 4 2's. So the 2 can come out. And the only factor left over inside is 1, since 1's a factor of everything. So 16 to the 1/4 is the same as positive 2. So let's say I ask for 27 to the 2/3 power. Well, again, the denominator is the index number. So we now know that the denominator is 3, so the index number is 3. And then the numerator is the power. So this would be 27 squared. Or the other way to look at it is I could say the cubed root of 27, and then I could square this. So we're going to work this out both ways. It doesn't matter which way you choose, they mean the same thing. Since the denominator is 3, that's our index number. So I'm looking for 3 identical factors, and there's a lot of ways we can do this. 27 squared, do not multiply it out. Do not multiply it out. Write out literally what it means. It means 27 times itself. Now we can factor or break those down, and there's a couple things we can do. I'm going to choose to say, well, 27 is 3 times 9, and 27 is 3 times 9. I can keep breaking the 9's down and factor them into 3's, or my index number is a 3, so I'm looking for 3 identical factors, and I'm going to happen to notice that this is exactly the same as 9 times 9 times 9. So I could rewrite it just to show you that this is the same as 9 times 9. And we know that that other 3 times 3, whoops, made a 9. Sorry, my pen's bleeding a bit. And so now the cubed root of 9 times 9 times 9 is simply 9. So 27 to the 2/3 power is 9. The other way we could look at it is we could say, well, this is the cubed root of 27 squared. So the cubed root of 27 is 3 times 9, which is 3 times 3. The cubed root of 27 is 3 times 9, but that's 3 times 3. Now we have cubed root. Try a different color here. Cubed root looks for 3 identical factors. So out comes a 3. Cubed root looks for 3 identical factors. So out comes a 3. And 3 times 3 is 9. So it really doesn't matter which way you happen to notice. It just looks at which way makes sense to you. So let's look at a couple more. So let's say I give you -8 to the 2/3 power. I'm changing my example. Well, the denominator is the index number. And this is -8. Now you have a choice. You could either say -8 squared, or you could say the cubed root of -8 and then square it. Well, if it's a negative, we're allowed to have a negative. So this could be the cubed root of -8 times -8. So 8 is 2 times 4. So I'm going to say -2 times -4, -2 times -4. Well, I don't have 3 identical factors yet, so I have -2. This -4, I'm going to say is -2 times 2. -2, -2 times 2. Now let's make sure this is still negative. 1, 2, 3, 4. Okay, where did I lose one? 1, 2, well, this -8. Oh, there it is right there. Oops. -8 is -2 times +4. Sorry. Somebody's already probably caught that already, but -8 is -2 times +4. Now do I have it? -2 times +4, -2 times +4. So pull out what we have that's identical. So I have 1, 2, 3 2s. So I can take out a 2. And I'm left with -1 times 2. Now remember, I took that one out, and that one out. I'm left with a -1 times 2. And I'm left with this other 2. What do I have that's identical? I have a 2, 2, and 2. So I'm going to take that out. I already had the 2 out here. And I'm left with a -1 times a -1, which is a +1. Cubed root of 1 is 1. So I'm just left with a 4. Now, hopefully that wasn't too confusing. The other is I could look at this as a -2 times a -2, which gives me a +4. This method says I have the cubed root of -8 squared. Cubed root of -8, we did earlier, 3 negatives make a negative. So the cubed root of -2 times -2 times -2, well, since I have 3 identical factors, I can pull out the -2, and now I can square that. So a -2 squared is still +4. So either way, I end up with +4. One activity, one thing I want you to practice is, I'm going to ask you to classify. Classify the number. Our choices are, make a little chart here. The choices are, is the number natural? Is the number whole? Is the number an integer? Is the number rational, which is actually a Q? Is the number real? And let's say I start with the number -2. Well, natural numbers are 1, 2, 3, 4, 5, so it is not natural. Whole numbers are 0, 1, 2, 3, etc. Integers are positive and negative whole numbers, so this is an integer. Integers are rational, rational numbers are real. Let's say we look at 3.4, 3 4/10. When in doubt, remember that's the same as 3 4/10. Is 3 4/10 natural? No, it's not a counting number. Is it whole? No. Is it a positive or negative whole number? No. Is it rational? Can it be written as a fraction? Yes, because this could be 34/10. Therefore, it's also a real number. Okay. Let's say I give you the square root of 7. Not natural. No child starts counting this way. It's not a whole number. Now remember, we did this at the beginning of class. This is a non-perfect number. So that means the square root of 7 is tucked between the square root of 4, which is 2, and the square root of 9, which is 3. So this is not rational, it's irrational, but it's still a real number. Okay. So there's all kinds of ways we can practice identification of real numbers. Now let's take a look at some properties, theorem where we use radicals. And the most common theorem that you've probably used in your past could be Pythagorean's theorem. Let's take a look at some application using square roots. Okay, so let's take a look at this. Pythagorean's theorem. Well, Pythagoras noticed that there's a relationship between a right triangle and the sides. So for any right triangle, ABC, line segments are always capital letters. Sorry, vertices are capital letters. Line segments are lowercase letters, where C is a right angle, 90 degrees. He came up with, if I take the sum of the sides and square them, that will always be the hypotenuse squared. So given a right triangle, where the right angle, that vertex is C. If I have other two angles, and we'll talk more about it in 3120. If this is angle A, it creates a side across from it, which is side A. If this is angle B, the two sides that make angle B create a side opposite it that is side B. And similarly with angle C, it's the largest angle, so it's going to produce the longest side. And that longest side is what we always call the hypotenuse. The other two sides, you either call them sides or legs. Side A or leg A, doesn't matter. So for example, find side C given the following triangle. Now, we're trying to find the hypotenuse, side C. It's always across from the right angle. I'm going to call this angle up here A. And side A is 12 because it's the one across from it. Angle B creates the side across from it. And I'm going to tell you that that's 9 units long. So because it's a right triangle, we know that the Pythagorean theorem works. So we know the two sides squared added together will always yield the hypotenuse squared. So side A is across from A, that's 12 squared. Side B is across from angle B, so that's 9 squared. 12 squared is 144. 9 squared is 81. 81 plus 144 is 225. And now to solve C, because it's being squared, we're going to take the square root. But if you remember, if we're the ones taking the square root, you always get a positive and a negative root. So the square root of C squared is going to give you C. The square root of 225 is 15 times 15. So technically our answers are positive and negative 15, but because we're talking about the length of a side, and we talked about this earlier, you cannot measure distance using negative. There is no ruler that has a negative on it. We can only then use the positive root and get square root of 15. 15, sorry about that. So let's find the value for X. Given that, here's my right angle. The longest side across from the 90 degrees is 6. One side is 2. One side is X. It may not be drawn to scale. That doesn't matter. We just need to figure it out. So because it's a right triangle, we know that Pythagorean theorem will always work. The hardest part's identifying the hypotenuse. Hypotenuse is always the one across from the 90 degrees. That's always the longest side. So now we know that x squared plus 2 squared will equal the hypotenuse squared. 2 squared is 4. 6 squared is 36. Subtract 4 from both sides. Now x squared is 32. And in order to solve that, we've got to take the square root of both sides. And whenever you physically take the square root, you get 2 answers. Square root of x squared. Well, index number is 2. I see 2 x's there, so I can pull out an x. I'm going to go straight for a perfect square. 32 is 2 times 16. And I already know the square root of 16. Square root of 16 is 4. With a 2 left over on the inside. Technically, it's positive or negative 4 root 2. But again, we're looking for the length of a side. Length can't be negative. So this is only the positive 4 root 2 or 4 radical 2. Now, let's do another one. But let's not have an integer or a whole number for the side length. Mathematics, it doesn't change. Concept doesn't change. The only thing that's going to change is what we're putting into the problem. So let's do this. Is the triangle a right triangle? Well, if the Pythagorean theorem works, then it's a right triangle. So let's start with this one. Let's say I give you a triangle. It looks like it's a right angle, but you don't have the symbol. So you cannot assume. But this is 2 inches long. This is 3 inches long. And this is root 14 inches long. So if a squared plus b squared equals c squared, then the triangle is a right triangle. That's the converse of the Pythagorean theorem. Instead of going if P then Q, we're going the other way. If Q then P. So let's check it out. Because it appears that, well, we know the square root of 14 is bigger than 2, because 2 squared is 4. We know the square root of 14 is bigger than 3, because 3 squared is 9. So the square root of 14 is between square root of 9 and the square root of 16. So this appears to be the hypotenuse. So let's check. Is a squared plus b squared equal to c squared? Is 3 squared plus 2 squared equal to the square root of 14 squared? Well, 3 squared, 3 times 3 is 9. 2 squared is 4. The square root of 14 squared is 14. Is 13 equal to 14? No. So this is a false statement. Since it's a false statement, then the triangle is not a right triangle. Not right triangle. And lastly, same question, is it a right triangle? But let's say I give you this one. And I'm going to tell you one side is 2 kilometers. One side is root 7 kilometers. And one side is root 11 kilometers. And again, square root of 11 is greater than the square root of 7. Square root of 11 is greater than 2. Because this square root of 11 is bigger than 9. Square root of 9 is 3. So this number is larger than 2. So it would appear as though this is our longest side. So this is our C value. So we're going to check. Is a squared plus b squared equal to c squared? Is 2 squared plus root 7 squared equal to root 11 squared? 2 squared is 4. Square root of 7 times the square root of 7 is 7. Square root of 11 squared. Square root of 11 times the square root of 11. Those operations undo each other. Is 7 plus 4 equal to 11? Is 11 equal to 11? This is a true statement. So therefore, the triangle is a right triangle. So we've taken a look at some real numbers. We talked about radical numbers, rational numbers, irrational numbers, and some application. All right, so that takes care of 7.5. And have a good rest of your day.